Welcome to You Got Hope Science. I'm Hope, and you're about to learn some science. So, in today's lesson, we are going to look at stuff passing through the cell membrane through what we call a passive process. So, what passive essentially means is there is no energy required for this substance to pass across the cell membrane. Now, in order to understand why it doesn't require energy, you need to understand something called concentration gradients first. So, if I had a high concentration of something, that would mean I'd have a lot of it. So, for instance, an easy analogy would be something like a really full bus would have a high concentration of people, and a really empty bus would have a low concentration of people. And generally, what particles want to do is move from high concentrations to low concentrations. So just like being stuffed into a room full of people, generally most people want to move out of that room because they feel too close to people. And the same thing is with particles. Particles want to spread out as much as possible. So there's really kind of three scenarios that we're going to look at here in terms of concentration gradients. The first one I'm going to do, I'm just going to talk about having a high concentration and then a low concentration in one direction, and then what would happen if it was even, okay? So let's imagine this line here is our cell membrane. And we're going to say everything up here is outside of the cell, and everything below here, this is inside the cell. So let's say we had a high concentration of some particle outside of the cell, and so these dots represent some kind of particle. Now, when we start going through today's lesson, we're going to be talking about things like carbon dioxide, oxygen, sugar, and water, more specifically, in terms of particles. So in this first scenario, I have a very high concentration of particles outside of the cell, and I have a very low concentration of particles inside of the cell. So it's called Brownian motion. Brownian motion is when particles want to spread out. So smells, gases do this all the time. So for instance, when you start cooking something that has a lot of smell to it, at first that smell is only going to be around the pan or around the oven. And then as time passes, the gases have the ability to start to spread out from where it's highly concentrated in the oven or the pan to the kitchen, and then from the kitchen into the living room, and then even outside of the building. Okay, so I'm sure we've all passed a house before and you can smell barbecue coming out, or you can smell different types of foods, the smell emanating from the house. That's diffusion. It's going from somewhere that is highly concentrated to low concentration. So for instance, because there's a high concentration of particles outside of the cell here, some of these particles are going to start passing through the membrane into the other side, inside of the cell, until their concentrations are equal. So in my next box here, I'm going to show what would happen when you reach equilibrium. So equilibrium would mean that we have equal amounts. Equilibrium is a topic we talk about a lot in biology as well as in chemistry and even physics, okay? So at equilibrium, what you would have is an equal number of particles on each side. So what I'm going to do is I'm going to draw 10 particles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the outside, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, on the inside and the outside. Now, because I have equal amounts of particles on the inside and outside of the cell, there isn't going to be a rush to move into a certain area. This is called equilibrium, where we have equal concentrations. Now, this doesn't mean that particles aren't going to move across that cell membrane, but what they're going to do is they're going to move across that cell membrane at equal rates. So as one particle maybe moves out of the cell, another particle is going to move in. If one particle moves out of the cell, another particle is going to move in. I always like to equate it to sports. So everybody's familiar with hockey, I would think. As one player comes off the ice, another player comes on the ice. There is an equilibrium. As long as the teams are at full strength, I have 5 skaters on the ice. One goes on, one comes off, and it's always going to be 5. That's a state of equilibrium. Now, the third scenario is I have a higher concentration of some kind of particle inside of the cell. And so I'll draw, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 particles here. And maybe I only have 5 outside of the cell. What would naturally happen is these particles would start transferring across this cell to try to hit equilibrium. We always want to try to get to equilibrium in terms of concentration gradients. If you need to try to keep the concentration gradients unequal, that generally requires an additional energy to force it to happen. Almost like if you had to force people to stay inside of a building that was really crowded, say there was bouncers actually trying to keep people in the building, they would have to use energy to force the doors closed and keep everybody in. That would require energy. But we're not talking about that today. We're talking about no energy. So particles generally flow from areas of high concentration to low concentration without the addition of any energy. And when we don't add any energy, this is called passive transport. So we need to have a basic understanding of these concentration gradients and how particles work before we talk about the individual processes, which of course there are going to be 3. So again, passive transport is the transport without the addition of any energy. Okay, now there's 3 types we're going to look at. We're going to look at diffusion, we're going to look at osmosis, and we're going to look at facilitated diffusion. Now, diffusion is generally with gases, which can just naturally pass through the membrane. They do not require a protein, an integral protein, or a certain type of channel protein to allow for the solution or the particle to move through. Whereas when we get to osmosis, we do need to have a channel protein. It's actually called an aqua protein to allow for water to move. And then in facilitated diffusion, we actually have to have an integral protein which kind of opens and closes like a door. So the first thing we're going to talk about is just diffusion. So I've got 3 scenarios here, and it's going to be very similar to above, but we're going to use actual particles, okay? So again, what I'm going to say is above here, this is outside the cell. And on the bottom, we're going to call this inside the cell. Okay, so I'm going to use an actual particle. I'm going to talk about oxygen, okay? So let's say we had lots and lots of oxygen outside of the cell, and we had very little oxygen inside of the cell. So we would say we have a high concentration of oxygen outside the cell and a low concentration of oxygen inside of the cell. Oxygen can pass through the membrane without the addition of a protein to do so. So these oxygens would actually naturally move through the cell membrane and into the cell. They want to have an even distribution of oxygen inside of the cell and outside of the cell. So they would continue to move in until they reach equilibrium. Now the thing about oxygen though, I'm going to tie this into our cell parts lesson, is that the oxygen is always being consumed. So the oxygen is being used up by the mitochondria for cellular respiration So when we do physical activity, our body and our cells take the oxygen that we breathe in, they react it with sugar in the mitochondria. That is then turned into carbon dioxide and water, which is then used to make ATP. And then that ATP is used to do physical processes. Now, because we're always doing physical processes, the oxygen is always being consumed. So oxygen really never reaches an equilibrium because we're always consuming the oxygen inside of the cell. So oxygen will continue to pass through the cell from outside of the cell into the cell because we are constantly consuming the oxygen. So there's our first scenario, a higher concentration of a type of gas outside of the cell and it's moving into the cell. Now, a type of gas which is inert and our bodies don't use for anything really, but we breathe in constantly, is nitrogen. So I'm going to call this an equilibrium scenario. So let's say we have nitrogen, 80% of our atmosphere, 79% of our atmosphere is nitrogen, and we breathe that in constantly. Every breath we take is about 79 to 80% nitrogen, and that still goes into our body, okay? So I'm going to say in this cell, I have an equal amount of nitrogen inside and outside of the cell. So it's not that the nitrogen won't move in and out of the cell, it's just going to do it at an equal rate. So if some nitrogen moves into the cell, then some nitrogen moves out of the cell. Now, I'll tell you when this scenario becomes a little bit different is if you went diving, okay? When you go underwater, there's a higher amount of pressure on your body and actually more nitrogen will diffuse into your blood. And so you'll actually get a higher concentration of nitrogen in your blood. And then when you come out of the water, that nitrogen needs to get released. And so if a diver doesn't come up slow enough, nitrogen can actually get trapped in the body, in blood vessels, etc. And you get something called the bends, which can be fatal, or you can lose limbs or have severe damage to different parts of your body. Okay. All right, so that is at equilibrium. Let's look at another scenario where we actually usually have a higher concentration of gas inside of the body. And so the one I'm going to choose here would be carbon dioxide. Now, carbon dioxide concentrations inside of a cell are generally higher than outside of a cell. So although we talk about, there's a lot more carbon dioxide in our atmosphere now, which is causing global warming, carbon dioxide actually makes up less than 1% of our atmosphere. Where all this carbon dioxide is coming from is from cellular respiration. It's the product. So when our cells use glucose and oxygen in cellular respiration, the byproducts are going to be CO2 gas, H2O gas, and energy in the form of ATP, which is going to get used up. So as the oxygen is being consumed, we start getting a much higher concentration of CO2 inside of the cell. There'll be very little CO2 outside of the cell because, again, there shouldn't be. So naturally what will happen is the CO2 will diffuse across that membrane outside of the cell to decrease the concentration of CO2 inside of the cell. So just like oxygen, but in the opposite direction, we really always have CO2 diffusing across the cell out of the cell because CO2 is constantly being made through the process of cellular respiration by the mitochondria. So again, here's our three scenarios. We have a higher concentration of gases outside of a cell, so then those gases diffuse into the cell. In this scenario, we would never reach equilibrium because the oxygen gas is constantly being used up by the mitochondria to produce energy. Here's our second scenario where we're actually in equilibrium. I picked nitrogen because it's an inert gas and our bodies don't use it for anything, but we do breathe it in. So nitrogen's going across the cell membrane both directions, but at equal rates. So if one nitrogen enters, one nitrogen would exit. In our third scenario here, we're constantly producing carbon dioxide within the cells because we're constantly doing cellular respiration to carry out all life processes. So now I've got CO2, high concentration inside of the cell. It naturally wants to move outside of the cell, and so it will continually be doing this, and it will never really reach equilibrium unless for some reason the CO2 couldn't escape. So what we've learned so far is that diffusion is generally used for gases to cross the membrane, and it does not require a protein, an integral protein, in order to cross that membrane. The second type of passive transport we're going to look at is osmosis. And osmosis is based all around water moving in or out of the cell. All right, now, because the phospholipid bilayer has a water-loving part, which is the phosphate head, water is attracted to the membrane, but there is a problem. It has a water-hating or hydrophilic tails underneath it. These are water-hating. Now, that's this part here and this part here. Now, because of that, water just can't pass through the membrane like gases pass through the membrane. They actually need a protein in order to cross the membrane. Now, this is a type of integral protein. And it has a special name because it's dealing with water. It's called a aquaporin. Now, there's three types of solutions that we're going to look at, and it's very similar to what we've done previously. So we're going to look at a solution where there is a equilibrium between the solution inside and outside of the cell. This is called an isotonic solution. Then we have a situation where the solution outside of the cell has a higher concentration of solute, which is called a hypertonic solution. And then we have a scenario where the solution has a lower concentration of solute outside of this cell, and that's called a hypotonic solution. So the first one we're going to look at here is going to be an isotonic solution. So again, I'm going to stick with this. Above the cell membrane is outside of the cell, and the area underneath is going to be inside the cell. So the term iso means the same. So what that means is the concentration of solutes in the solution outside of the cell has to be equal to the concentration of solutes inside of the cell. So I'm gonna draw 5 circles outside of the cell. So these are going to be particles in the solution outside of the cell. And I've got 5 particles inside of the cell. And these are dissolved in water. So they're surrounded by water. So what will happen is water will flow at an equal rate out of the cell as inside of the cell, because what the water wants to do is to have those solutions at equal concentration. And in order to keep them at equal concentration, water will move into and out of the cell at equal rates in order to maintain that. So we would call this an isotonic solution. Water will move in and out of the cell, but at equal rates. And so the concentration of these particles into and out of the cell is going to be equivalent. Easy enough to understand. Let's talk about a hypertonic solution, and I'm going to talk about it as a hypertonic solution outside of the cell. So again, the top of the cell is going to be outside of the cell. The bottom of the cell is going to be within the cell. Okay, so if I have a high concentration of solutes outside of the cell, so I'm going to draw a lot of particles outside of the cell. Okay, and I only have a few particles inside of the cell. And I want you to remember there's water all around these particles. These are dissolved in solution. So out here I have a very high concentration of solution, and inside I have a very low concentration of solution, but I have, say, equal amounts of water. What will happen is water will start to leave the cell by osmosis to try to get the concentrations equalized. So I'll say this again. Let's say this is 5 particles per 1 milliliter, and that's the ratio. And out here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's go with 15. Let's say there's 15 particles per 1 milliliter. What water is going to do is it's going to move out of the cell until these ratios are equal. Okay, so I would have 20 particles total per 1 mill. Well, I got 20 particles total in 2 milliliters. So what will happen is water will leave the cell until the ratio becomes 10 particles per 1 milliliter, because that would be an equal amount of water per particle on each side of the cell. Now, what will end up happening is if this was my cell and I start to lose water out of the cell and I have more water leaving than entering, what will eventually happen is this cell is going to start to shrivel up and die. It will continue to lose that water until the cell will actually start to shrivel up. So if you put, say, certain plants in a highly solute concentrated water that it's not used to, it will actually lose water and it'll start to shrivel up. Here's another weird analogy, I guess not an analogy, or story about going into a hypertonic solution. Fighters, boxers or MMA fighters, have to fit or fall under a certain weight category, and normally they train at a higher weight. So let's say I fight at 150 pounds. Normally, day to day, they're probably somewhere 155 to 175 pounds. And then they have to lose weight to make their fight. So you'll hear about them going in saunas, so they sweat out a bunch of their water weight. Or something else they've been known to do is to go into a bathtub full of Epsom salts, so highly concentrated salt water, and their body will naturally lose water into the bathtub, and they will lose water weight this way. So their body is essentially acting like a giant cell, and because there's a higher concentration of solutes outside of their body in the bathtub, their body will start to lose water into the bathtub. Another scenario, I hope all of you have heard this, is not to drink salt water. When you drink salt water, you actually become more dehydrated. And so what happens is, when you drink the salt water and it enters your body, here's a cell in your body, and I've got all the sodium chloride, magnesium chloride, calcium chloride, salt water around my cell. What will happen is there's a higher concentration of water in here. It starts to lose water to the water you drank, which is full of these salts, and you actually become more parched and more dehydrated. That's why we can't drink salt water, because it actually dehydrates the cells in our body. Our third scenario is if we had a hypotonic solution outside of the cell. So in this case, we would have, say, I'm going to stick with 5. We have 5 particles in 1 milliliter outside of the cell. And then I'm going to say that we have 15 particles inside of the cell for every 1 milliliter. And so the water wants to equalize the amount of particles per milliliter. And so water will rush into the cell. Now, what will happen here is if I have my cell, water is going to start rushing into the cell, and the cell is actually going to expand and get bigger. And it can actually get to the point where the cell membrane can't even hold itself anymore. The pressure is too much, and it will actually break the cell and destroy the cell. So basically, we have a low concentration of solute outside of the cell, and we have a high concentration of solute in the cell. And so water will rush into the cell, making the cell expand and get bigger. Now, when we think about plant cells have a rigid cell wall. So if we water a plant the correct amount, those large vacuoles inside of the cells will expand. It'll give the the plant cell rigidity, which is Tuger pressure, and make the cell nice and plump and firm, and it'll have nice firm leaves. Okay. Now, if we overdo it with some animal cells and there's too much water rushing in, the cell can actually expand and explode. So the way I remember the difference between hypertonic and hypotonic is I always say hypo has a low concentration of solute. Hyper has a high concentration of solute. So this is osmosis. Osmosis is the no energy movement of water through aquaporins inside and out of the cell. And the way it moves and how much it moves depends on the concentrations of solutes inside and outside of the cell. So if outside of the cell has a very high concentration of solute, water will rush out of the cell to try to equalize those concentrations. In doing so, the cell will actually end up shrinking and possibly dying. If the concentration of solutions inside of the cell is higher than outside of the cell, water will naturally rush into the cell, causing it to expand. And if there's too much solute, it could even break the cell membrane. The last type of passive transport we're going to look at is facilitated diffusion. Generally, facilitated diffusion is used for larger molecules. They use integral proteins, which could be either a channel protein, sort of like the aquaporin, or a carrier protein. Now, a carrier protein is like a door with a specific lock and key mechanism that allows the door to open up. So a good example of facilitated diffusion is the crossing of glucose across the cell membrane. Now I'm going to stick with this being outside of the cell and this being inside of the cell. Generally, there is more sugar or glucose, which is C6H12O6, outside of the cell than inside of the cell because it's constantly being consumed by the mitochondria to make energy, carbon dioxide, and water. So I'm going to call glucose like a blue circle here, okay? So the door itself is going to be able to take this circle and activate the protein to open up. Just like when you put a key into a lock, it activates the lock to then open up. So I'm just going to draw a rough sketch of maybe what this protein looks like. The protein would have to have a shape to accommodate that particle. So in this case, I'm making kind of a circular shape in order to allow that circle to enter. So I would have a higher concentration of sugar outside of the cell. The sugar would hit the protein and fit into that space like a key. This is the protein being the door and this being the key going into a lock. The protein then closes around that particle, and in this case, the particle would be sugar, encasing it, and then opening up so that the glucose molecule could go into the cell, and the door would just be opening the other way. And then what would happen is this would then reset itself and open up facing outside of the cell, so it's ready to take another glucose in. It's a one-way door or one-way street system. So to be clear, this would enter, it would lock around that particle, the door would then open up so the particle could leave, and then the door would readjust to look like this again, to be ready to take in another sugar particle or whatever special particle it is. Channel proteins are like just an open door. Channel proteins just allow for the flow of something to move in and out of it, but there is no locking key mechanism. It's just an open gate, and the particles will flow into and out of it based on concentration gradients, going from high concentration to low concentration. I hope you've enjoyed this lesson of You Got Hope Science. See you next time.